All right, Calc BC students, welcome back to your crash course in parametric equations. I want to concentrate on physics and get all the physics equations down, and hopefully you'll recognize most of these. Okay, so let's say we start off with position. So I've got position, and I've got some my x component and my y component as a function of time. Okay, so if I have a point in space, so this is my xy point, both as a function of time, then I can actually define the magnitude of the position, which would be my radius from the origin, and my angle theta. And you may remember doing this in physics. So the magnitude of position is going to be equal to, I'm just using the Pythagorean theorem, is going to be x as a function of time squared plus y as a function of time squared. And my direction, theta, is going to be equal to the inverse tangent of my y as a function of time over my x as a function of time. And so this gives me both my magnitude of my position and the direction of position at any time as a function of time. What's more useful is oftentimes we're given the velocity components. And so if I'm given the velocity components, let's say v sub x is a function of time and v sub y is a function of time, then as long as I know, so you have to know the position at some initial time, which could be 0, but doesn't have to be, and I know my position in the y direction also is some function of, or some value, initial value of time. So I know my x position and my y position at some time. Then I can use the fundamental theorem of calculus in order to determine what my position equations are. So for example, let's say I'm given the x component of velocity, and I'm given some known position at a known time. So that's all I need. Then what I can do is I can calculate my position as a function of time is equal to that known x value at time a plus the integral from time equals a to time equals t of my velocity component in the x direction dt. And similarly, I can find my y position by having my known point plus the integral from time equals a at the known point to t of v sub y t, the y component of velocity. And so this is a very useful relationship if you're given velocity and you want to find position. Okay, now let's look at the velocity relationships. All right, so let's say I have velocity, or I want to find the velocity. And so that's going to be v sub x as a function of time and v sub y as a function of time. So the x and y components of velocity. Well, if I'm given position, that's relatively easy, because if I'm given position, then I just need to differentiate the position with respect to time, and that will give me my velocity as a function of time. So that's just going to be x prime of t, comma y prime of t. But if I'm given acceleration, so if I'm giving the acceleration parametric equation, so a sub x as a function of time and a sub y as a function of time, then I'm going to have to know one piece of information about the velocities. So I need to know v sub x at some time t equals a, and the velocity in the y direction at some time equals a. Then I can use the fundamental theorem of calculus in order to determine the velocity. So v sub x as a function of time would be equal to my v sub x at known time a plus the integral from a to t of a sub x of t dt. And similarly, my v sub y as a function of time would be equal to my known initial point in the velocity in the y direction, plus the integral from a to t of a sub y time dt. Okay, now with the velocity, again, if we want to find information about y versus x, whatever this graph may look like, then I can still use those equations that we developed. So dy dx is equal to dy dt over dx dt, which is equal to y prime of t over x prime of t. And if I wanted to find a second derivative, which gives me information about concavity, remember that this would be equal to d dt of dy dx from above, all over dx dt. And so I can still use those equations as well. Now, more importantly, is if I want to find the speed at a certain time. And so the speed is the magnitude of velocity. Remember, that's a scalar. And so let me write that down. So that's the magnitude of velocity. All right, and so in space, if I have Vx and a Vy, I'm drawing these both in the positive directions. Remember that the direction the particle is traveling in, you can tell by looking at the sign of the velocity. So if Vx is positive, then that means that the particle in the x direction is traveling to the right, and if it's negative, it's traveling to the left. But if I look at the Vy component, if the Vy component is positive, it's going up, and if it's negative, it's going down. But what I want to do is I want to find the magnitude of velocity, which is the speed. And remember, to do that, I'm just adding these two vectors. And so I've got my magnitude of my velocity, which is my speed, and my direction is theta. All right, so the equation for speed is the same one we used in physics. So the magnitude of velocity, which is the speed, is going to be equal to the square root of Vx squared plus Vy squared. It's sometimes helpful to write it as the square root of x prime of t, quantity squared, plus y prime of t, quantity squared. And that's my magnitude of velocity, or my speed. And then if you want to find the direction of the particle in terms of theta, then theta would be equal to the inverse tangent of Vy over Vx. Okay. Now, the other thing that's really important with velocity is if we want to look at the arc length along the curve, which is really, I want you to look at this instead as distance traveled. So if I have y versus x, and here's my particle path, let's say I want to find the distance it travels from some point A to B. All right, well, we developed the equation before in chapter 7. So the arc length is equal to the integral from x1 to x2 of the square root of 1 plus dy dx squared dx. But we really don't want to use this because we want to figure out what the arc length of the distance traveled is in terms of time, not in terms of x. And so if you remember from Calc 1, the distance traveled is equal to the integral from t1 to t2. Now, we called it the absolute value of velocity. And really, this absolute value of velocity is really the magnitude of velocity, which is the speed. So in two-dimensional motion, we can write this as the integral from t1 to t2. And I know my speed equation is up here. And so this is going to be the integral and then the square root. There we go. The square root of Vx squared plus Vy squared as a function of time, dt, which is also, it's helpful to write it as t1 to t2 of the square root of, I can write this as x prime of t, or dx dt, whichever you prefer, squared, plus y prime of t, or dy dt squared, and that's with respect to time. So now I've got my arc length, or the distance traveled along this path, as a function of time, not of x, which is a lot more efficient. Okay, so the last thing we want to do is look at acceleration. Okay, so the acceleration parametric equation is going to be a sub x as a function of time and a sub y as a function of time. So that gives us our acceleration in the x and y directions. Now sometimes you'll be asked if a particle is slowing down or speeding up in the y direction, for example. And so you'd have to find the acceleration component in y and also the velocity component in y. And remember, if the signs are the same, then it's speeding up. If the signs are opposite, it's slowing down. Now, typically, if you're not given the acceleration, you have to find it. And you have to either find it from the velocity or the position. So if you have to find it from the velocity, then remember that the acceleration is just the derivative of the velocity. So the x component of acceleration would be the derivative of the x component of velocity, and the y component of acceleration would be the derivative of the y component. Or if you're given position, the acceleration is the second derivative of the x position, acceleration in the x direction, and the acceleration in the y direction is the second derivative of the y position. And then you could also be asked, what is the magnitude of the acceleration? And magnitudes are always the same. So magnitude is, using the Pythagorean theorem, it's going to be ax squared plus ay squared. And basically what that does is, if you have, let's say my acceleration component in x is to the right, and my acceleration component in y is down, then the magnitude is going to be the sum of those two vectors, which we have to use the Pythagorean theorem for. And then if you're asked for the direction, then that's just inverse tangent of ay over ax. Okay, so this is kind of a quick crash course in parametric functions and 2D physics. And so what I'm going to do is I'm going to actually write out an example and email it to you, so you can kind of go through that. And I'll try to make it kind of a little bit of a challenging example, so you can kind of walk through it. So I'd recommend watching these videos again, because there's only about 35 to 40 minute video in total, and make sure you get all the equations down, and then start doing the problems, and let's go from there. All right, I'll see you guys in about a week. All right, take care, bye.